Welcome to Peninsula Seniors Out and About. We're at the Western Museum of Flight in Torrance. Let's go see what Cindy has for us today.
Welcome everyone to the Western Museum of Flight. I'm Cindy Maka, the director. Graduate of the United States Test Pilot School with thousands of hours in multiple aircraft types, flying hundreds of missions as both an operational pilot and test pilot, his career included the fascinating work that is of special interest to us today, wherein he was a test pilot for the X-29A Forward Swept Wing Experimental Fighter Program. Oh, and by the way, as you know, naval aviators all have radio call signs. Captain Schroeder's call sign is bulletproof. So now I'm going to turn the podium over to Captain Kurt Bulletproof Schroeder. So please wait until I duck out of the way and then feel free to throw anything at him. Thank you. Bulletproof, the podium is yours.
Good morning. First of all, I'd like to just express my appreciation for the kind invitation of Cindy and crew to come and talk to you about the X-29 this morning. When I got into trying to put something together, it became very clear to me that the concept or all the details of the program, we'd still be here ordering dinner in order to go through it. So what I've chosen to do is, for you engineers out there, I'm not going to present a lot of data. And instead, I'm going to attempt to give you just a little background on how the airplane came to be, and then the particular flight test issues that it presented during the program. What is an X-airplane? Well, an X-airplane is an opportunity to evaluate potential production technologies that can't be evaluated in a laboratory. Some of these lend themselves well to doing it in a laboratory, but aerodynamic initiatives are more difficult. They typically used, at that time, wind tunnels. The wind tunnels had limitations and potential scaling effects. And then when you have a vehicle that has interacting technologies, it defies accurate predictions obtained strictly through ground testing. So the ideal answer to validating these concepts is a full-scale test vehicle. First of all, X-airplanes do not normally include plans for production. They instead are hand-built specific research vehicles. The X-29 represented the first significant X-plane project in the USA for nearly a decade and a half. Some examples of previous X-series airplanes that you may be familiar with was the X-1, which was the first airplane to fly supersonically in level flight. That happened in 1946. The X-2 was the first aircraft to reach Mach 3. That happened in 1952. And then the X-15 was a hypersonic research vehicle that actually set many aviation records. So a little background on the genesis of it is, as the airplane performance began to push toward the transonic area, and this was really in the World War II era, it was determined that sweeping the wing provided benefits as far as delaying the drag rise that occurred with supersonic or transonic speeds. They also knew at the time that the drag benefit existed regardless of the wing sweep direction. However, a structural consideration dictated that aft sweep be the design criteria as opposed to the forward sweep. The problem with the forward swept wing was recognized is it had a structural phenomena called structural divergence. And to try to explain what this really means, it just says if you can visualize an aft swept wing, when it's loaded aerodynamically, the wing had a tendency to twist leading edge down, which would reduce the angle of attack, or essentially the direction of the wind, how it impacts the wing. It twisted down and therefore relieved the load on the wing. It was self-relieving. The forward swept wing, conversely, had a tendency to twist leading edge up, and that would increase the local angle of attack and therefore the wing load, and this would, in rapid progression would be, as we'll get in later, causes additional bending and loads on the wing. The only way at the time to avoid this characteristic was to build the wing so stiff that it would not twist, it would resist twisting. But that added considerable weight to any design that you wanted, and it really obviated the advantages of it. This is just a quick picture. You can see of the structural divergence of the wing on your left, that it twists the leading edge up as opposed to the other way around. There were prior applications to this, and unfortunately this particular one was happening in Nazi Germany. And basically they built an application here. You can see it first flew in the final stages of World War II, 1944. Interesting enough, they used an existing aircraft fuselage. They used a nose gear from a down B-24, so part of the U.S. was in the airplane. But basically, their motivation in this was not necessarily the aerodynamic benefits of the forward swept wing, but as you can see here, what it does is it puts the wing box of where the wing transitions through the fuselage, it moves it well aft on the fuselage of the airplane, which allowed the bomb bay to put up forward near the center of gravity of the entire vehicle, and which would allow them to carry a large weapon and then drop that weapon and not encounter a severe change in the trimming of the airplane. I'll let you decide what that large weapon could have been. As we all know, they were working on a nuclear weapon. We now go post-war. This is 1964. A German company built a general aviation, actually a corporate aviation airplane, the Hansa Jet. It incorporated a forward swept wing. Their desire, too, kind of went along with what the bomber people were looking for, because the wing box then would be further aft in the airplane. So from a cabin standpoint, that they could, number one, they wouldn't have people having to crawl over a wing box going through the airplane. And secondly, they could actually make the fuselage a little bit smaller in diameter because of the additional room. They built 47 of them. Interesting enough, part of the design lead on the Hansa Jet were people that had worked on the military version of the bomber. So evolving technologies, what happened in 1975, a Air Force Lieutenant Colonel at the time, Norris Krohn, authored in his PhD thesis the use of composite materials to solve the structural divergence problem. And what it offered was the composite construction could be, number one, it was low in weight, high in strength, but the layup of the orientation or the thickness of the plies in the construction of the wing could be tailored to resist the wing twist, which was the culprit they were trying to eliminate. The concept became known as aeroelastic tailoring, and it offered the potential to, for the first time, to realistically deal with a forward swept wing divergence problem in high-speed maneuvering environment. So the X-29 was born. DARPA and AFFDL, I'm going to use some acronyms here. If someone afterwards wants me to tell you what they mean, I'd be more than happy to, but I won't burden with you at this time. They proposed to build a full-scale airplane to evaluate the concept of a forward swept wing. They put out a request to 3 major aerospace companies, competed for the contract award, and Grumman was awarded the contract in December of '81. And important, as you'll find out in a little bit, is it was a fixed price contract. And I'll get into what the importance of that one. The contract details 2 vehicles were to be constructed. Both of them were going to be made in the Grumman plant in Bethpage, New York. Grumman pilots would perform the first 4 flights on the airplane to establish the flight safety of the concept, and then ownership of the vehicle would transfer to the government. Following that transition over to the government custody of it, the aircrew rotation consisted of both NASA, Air Force, and Grumman pilots. So this brought up the question of where to test the airplane. Since the airplanes were being manufactured and put together in New York, Grumman proposed to fly at least the first 4 flights, if not more, at the Calverton facility. Their argument on their side was the fact that we had a dedicated facility, we had an unimpeded test range, and we felt we could proceed further and get the first 4 flights completed. So the government was very hard over on, they wanted all the flight testing to be done at Edwards. And there was a lot of back and forth about the weather, the winds, and everything else. But the real determinant was the fact that people, I'm sure you're familiar with Edwards, they have dry lake beds in the test area, and they offered the opportunity, should we have a problem with the airplane, of getting it back on the ground on a dry lake bed, whereas our test facility in New York was out over the Atlantic Ocean. So obviously the airplane could not be recovered. So what I call the golden rule, them that have the gold make the rules, and so it was decided all the flights would be done out at NASA Dryden. So that raised the next one, how to get the airplane out there. So the airplane has a wingspan of 27 feet, so they looked at putting it on a flatbed, and obviously it couldn't go flat on the flatbed, it had to be in a fixture on an angle, but then the height of it caused all kinds of concern about the ability to get it across country. So that was rejected. They looked at a Super Guppy, they looked at the C5, a whole lot of things. Well, it turned out the ultimate solution was to ship the airplane out via ship. And so it was loaded on a freighter in New York and came to Southern California on a boat. So the next problem that Grumman had is that we had to send a lot of people out to the desert in order to support the airplane. It quickly became common knowledge among the troops was that California did not offer the cherished Long Island delicatessens. So we had to do something about it to try to encourage these people to volunteer to come out and support the airplane. They made a poster. Anybody familiar with the airplane knows that this is a little stretch of the truth. Okay, agencies involved with this program. This is really fairly unique. Once again, we have a whole bunch of acronyms up there, and it's not important that you understand what each one means, but it is important to know that some represent the federal government, some represent the testing environment, some represent the Air Force, and then of course you have the private contractor and NASA. So this is an integrated test team, but I can tell you that when anybody saw this, they said, this is not going to be easy because of all the various agencies involved. Part of the success that Grumman had, this is my personal belief, in winning the competition, is they approached it as what we would call a junkyard dog approach. The engine is a GE 404, which was used in the F-18 at the time. The hydraulic actuators came out of the F-16 program, the flight computers from the SR-71. The forward fuselage was a F-5 forward fuselage. The main landing gear came off an F-16, the engine accessory package as well from the F-16, the EPU F-16. And so we ended up with an airplane that was 27 feet with a wingspan, 48 feet in length, 14 feet high, and at empty weight it was around 13.6 with a takeoff weight around 17.6. This was another stroke of genius in my mind, is they said, look, we're going to build a vehicle to test the forward swept wing concept. But to make it a more useful program is we would like to introduce additional technologies into the airplane in addition to the forward swept wing. We're going to cover each one of these because it's important for you to understand the concept of the airplane. In essence, the obvious one is the forward swept wing. It identifies the airplane to everybody else, but the other items, we'll cover them one by one. Stand by, this is the data that I'm going to present. This is the only data slide I have, and I know it doesn't tell you a hell of a lot. What it is, over on the left side, is the lift coefficient. On the right side is the drag. Lift is good, drag is bad, and as you can see, the forward swept wing was anticipated to be considerably better for a certain lift coefficient, which is what you're either supporting the airplane with or maneuvering with the airplane, that you would have less drag. And that compares a forward swept against a similar aft swept wing. First one of the technologies is a aeroelastically tailored composite wing. It's composites laid up to resist the twist and everything, but in addition, it was a thin supercritical airfoil. Now, you may have heard of a supercritical airfoil because it was used on primarily commercial airliners. And what it does is it modifies the profile of the wing to delay the transonic drag rise. So it allows the airplane to cruise at a higher Mach number. But it had never been applied to a wing as thin as what we had on the X-29. The close-coupled canard, you're probably all familiar with what a canard is. It's a wing that's forward on the airplane. But basically, this is just a picture of a traditional airplane, which is on the bottom. When you're maneuvering that airplane or you're trimming that airplane, you're putting a load on the horizontal tail or the elevator, whichever it has. But that load is directed down. That's lift you're generating to control the airplane. And that's adverse because any lift that you're generating has drag associated with it. A canard being up forward and everything, its lift is generating in the proper direction to add to the additional lift on it. So why doesn't everybody have a canard? In a general sense, canards are destabilizing, which we'll get into as well. But as you can see, in a number of the current fighter aircraft in the world, there's a lot of them that employ a canard. What were the challenges of this vehicle when we now are going to decide, okay, we're going to test this airplane? What do we have to deal with? First of all is the static instability. The aircraft subsonically was 35% unstable. This may not mean a lot to everybody, but basically the current modern day fighters employ what is called relaxed static stability. And why is that? Is because stability, while it's great for a transport airplane flying around, for a maneuvering fighter airplane, anytime you want to maneuver, you have to overcome the basic stability of the airplane. So typical modern day fighters might be in the 5% unstable region. So it was said that the X-29 is not relaxed, but it's unconscious. So anyways, the other aspect is, and this applies to any wing, when it achieves supersonic flow, the center of pressure on the wing moves from quarter chord to half chord. And it's not important that you understand that, but what it does is it results in an apparent increase in longitudinal stability. Once again, if you want to maneuver the airplane supersonically, that's not good. So the X-29 being 35% unstable subsonically, it achieves nearly neutral stability longitudinally when supersonic. To give you an idea of what the ramifications of the 35% unstable is, it's defined by a term called time to double amplitude. What this means is that when the airplane is disturbed, and let's just say for the sake of discussion that it pitches up 5 degrees, without with all the controls frozen, when it reaches that 5 degrees, in a little over a tenth of a second, it will go to 10 degrees. And another tenth of a second, it will go to 20 degrees. And another, it gets to the point where you don't much care anymore. But basically, most fighter pilots will say, I can fly that airplane. Trust me, you cannot. You can't react quick enough in order to control that level of instability. Now, in some programs where they're dealing with stabilities and what have you, they choose to ballast the test airplane to a forward CG, which gives them a larger longitudinal stability. And then progressively they remove some of the ballast out of it and work their way back to lower levels of stability. So that was kind of suggested for the X-29 might be a reasonable approach. When they did the calculations, they determined that we'd have to hang a Volkswagen on the nose boom of the airplane in order to achieve neutral stability with the airplane. Riding to the rescue, fly-by-wire control systems, which I'm sure is a very common term now. Most people know about it, but basically all you need to understand about it is the pilot no longer commands the surfaces. He has no connection to the flight control surfaces on the airplane. All the pilot does through the stick and rudder conventionally, he sends electrical inputs to a computer. Then the computer says, okay, I know what you want the airplane to do, and then it acts through its control laws and calculates the proper deflection of whatever surface it needs to achieve that maneuver in the airplane. Obviously, the fly-by-wire systems are in the current airplanes, the F-18, the F-16, and so on. The fly-by-wire technology was initially developed using analog flight computers, and the obvious next step was to go to digital computers. But at the time, when they were going through all this stuff, the faith and confidence of digital computers had not reached the stage that it has today. The incontrovertible thing is the control of the X-29 was totally dependent on a functioning flight control system. Loss of the flight control system would result in a tumbling aircraft within seconds. Now, let me understand, people I'm sure have heard of, in the aviation industry, of airplanes departing. And they depart controlled flight. Most airplanes, when they do that, they will depart in yaw. There may be some pitch activity and what have you, but when we're talking about the X-29 and tumbling, it literally goes like this. So not a pleasant experience for anybody in the airplane. Within seconds, if it was dependent on speed, and if you were at a high speed, we're talking about less than a second. If you're at a slower speed, as we'll see a little bit later, it buys you a little time, but we're still dealing with seconds. So digital systems were clearly the future, but the confidence wasn't there. So consequently, the X-29 used a digital system, but also incorporated an analog backup system. It just so happened that the SR-71 had these type of computers, and that's what went into the X-29. It was a 3-channel system. Most modern-day airplanes have, in fact, all have 4 channels. Each channel of these 3 channels had independent sensors on the airplane, allowing the comparison between these different channels before sending commands to any actuator. So each channel receives its own sensor inputs. Each channel calculates the proper output to the actuator. The 3 channels then compare the output values, and if they match, the command is issued to the actuator. If one channel disagrees, but the 2 others agree, a fault is declared, but that value still is sent off to the proper actuator. What I choose to call a committee meeting, of having this meeting and saying, what is your solution? And then comparing them, happened 40 times each second. So the engineers got involved at this time, and they said, well, wait a minute. What happens if the system was very dependent on rate gyros? And so they said, what happens if on the 3-channel system, 2 of the rate gyros fail simultaneously and both have a null setting? Well, suppose that happens, and now we're at our committee meeting, and so the 2 guys with the bad actuators say, I got a 0, and I got a 0, and the other guy's got the proper one. They're going to say, well, you're obviously wrong, and they'll throw him out. And then we had backup gyros. They would go to the backup gyro, and the backup gyro would come back in with the proper solution, but once again, it'd get rejected. So it was a concern, and basically it was, the decision was made that through the proper or continual monitoring in the ground station of the gyro health, that we could live with it. Very unlikely that 2 gyros would go to null simultaneously. Okay, so we're going to get into the longitudinal control system of the airplane. And what differentiated the X-29 from typical airplanes is normally on an airplane is you have either elevators or horizontal tail that controls the pitch axis of the airplane. The X-29, in addition, had 3 different surfaces. I'll describe these a little bit, but they consisted of the canard, which we touched on just briefly, variable wing camber, and strakes, and they were active throughout the flight envelope, and I'll try to explain what each of them did. The integration of these allowed the airplane to be in the optimal aerodynamic configuration depending on what the flight regime is. We're all familiar with flaps on the back of the airplane, which are normally used for takeoff and landing and what have you, but these were surfaces that were active through the whole envelope of the airplane. So first we'll talk about the canards. The canards were nearly coplanar with the wing, and what that means is, okay, where are they located on the fuselage of the airplane? As you can see on the model, that they're forward up here, and the question is, where do they want to be in relation to the wing? And Grumman's position was that in this position they would actually help for the interaction with the wing and add energy, which would be beneficial for the performance of the wing. The canards ended up to be 20% of the wing area. If you look at current airplanes with canards on them, they tend to be kind of tiny little canards. 20% of the wing area is not a tiny canard. The travel on the actuators for the canards was 30 degrees leading edge up and 60 degrees leading edge down. So 90 degrees, and the actuator rate was 90 degrees per second. So in 1 second, they'd go from full up to full down. The airflow off the canard adds energy over the flow of the top of the wing. And here's the thing that a lot of people don't realize about the X-29 is the canards are what caused the instability. It wasn't the forward swept wing. The logical assumption is that much problem with a forward swept wing is it creates instability. Well, that's not true. The benefit of that is if you ever get in a flight regime where the canard stalled, that the wing body combination, which is what's left on the airplane that's generating lift, is essentially neutrally stable, much easier to control. Variable wing camber. Basically what this is, the X-29 had no leading edge devices on the wings. The trailing edge had these what are called variable camber, and they were, in Grumman's terminology, they could be called flaperons, what have you. But they're active through the whole thing. So they act symmetrically to determine the lifting capability of the wing, and they were used differentially to control the airplane for rolling maneuvers and things like that. Once again, active throughout the envelope. So camber, which I'm sure all of you realize, it's a lot of camber in the wing is really good for low speed performance, but you don't want a lot of camber at high speed. So this gave us the ability to have it depending on where the airplane was in flight condition. And the third one are the STRAKES. They're way back on the back end of the airplane, and they are not as quick reacting. You could think of them more as trimming surfaces. They didn't have the actuator rate or what have you, but they were used for things like takeoff, and they were active through the whole thing. So you have these three technologies that are interacting constantly. And of course, it's the control laws in the computer that are commanding them. Simulation was big on this program from the beginning to the end. The flight control laws were validated on the Grumman simulator in Bethpage. We also used CalSpan's, what is known as a TIFS, Total In-Flight Simulator. And then out at NASA, they had a simulator which was integral to troubleshoot anything we had, but also to pre-fly any of the flights, which turned out to be really beneficial because it increased the efficiency of any flight. You knew exactly what maneuvers you're going to do. You could even plan, okay, I'm going to head eastbound because I got to do this. Now I'm going to turn here, turn there. So it was very beneficial. Next one is the TIFS. It's not the airplane you'd like to go home when your parents are seeing you flying for the first time. It's ugly. But what it was is this forward cockpit is grafted onto the 131, and all the control laws and everything else reside within the parent airplane. And so basically when you go into that mode, you're in the forward cockpit and you could fly what was the control laws destined to go into the X-29. The only limitation was it really is a low speed simulator, but it was very useful for primary landing and approaches. Data analysis, that's the purpose of the whole program, is the data that it spits out. Real-time data analysis made expeditious envelope expansion possible, because at every test point that we went to, there were numerous things that people were concerned about that had to be analyzed to make sure that things were tracking predictions and we weren't going to go over a cliff. The real-time thing is the only thing that made that possible. An example of this is a normal flight control system stability criteria for phase and gain margins. They were reduced by 50% for this program based on the real-time data analysis. So we could live with lower levels of margins, if you will, to fly this airplane. The data analysis is for all the flights. Not only did we use the NASA ground station located up at Edwards, but they had a satellite link to the Grumman ground station in New York. So in the airplane, you had more people watching over you than you'd ever really like. But then again, they were the people that were going to make sure you get home, because everybody had a discipline and everybody had to give a thumbs up at every flight point that we were at in the sky and before we proceeded. So the program began. The first flight was on December 14th, 1984. Our chief test pilot, Chuck Sewell, flew the airplane. It was essentially an uneventful flight. Everything went as programmed. There was a lot of sensitivity to the weather conditions before we chose to fly it and everything else, but everything worked really, really well. So what challenges we were facing here is obviously we wanted to avoid structural divergence and other aeroserval elastic issues, which I'll get into. We had to control the longitudinal instability of the airplane because nobody wanted to go tumbling through the air. We had to achieve and support a reasonable reliability and availability for a one-of-a-kind airplane. NASA's had numerous X programs and what have you, and they necessarily were very, very, their availability was very difficult because they're hard to support. And we didn't want that with the X-29. The important thing, we had to acquire the data for an accurate assessment of the incorporated technologies and to do it as safely as possible. Here's one of the things we faced with it, is the airplane had an EPU, which is an emergency power unit. And what that says is if the engine quits on you, the EPU is powered by hydrazine, has the capability of providing hydraulics and electric power to the flight control system, which was absolutely required, and allow you to dead stick the airplane into a field. And once again, in addition to the normal runway, we had all these dry lakes and what have you. I know when people first see this, you say dead stick. That, my God, are you out of your mind? But as the shuttle demonstrates every time it came back and landed, is once you are proficient in handling the energy and what have you, it's no big deal. We practiced it primarily with the T-38, but we also did some approaches with the X-29. Every pilot in the program felt confident that they would be able to get the airplane back on the deck. However, the limited hydrazine created situations where the EPU runtime could be insufficient to reach that runway. This was not good because if the hydrazine ran out and you lost electrical power or you lost the hydraulic power, the bad things are going to happen with the airplane. It's going to depart. So the engineers sat down and they said, okay, well, what's reasonable? How are we going to get around this problem? And so they said, they did a calculation. They said, as long as you're no faster than 224 knots, which is relatively slow, the pilot would have 3 to 5 seconds to eject before the airplane reached 6 Gs, plus or minus. Now, when the airplane departed, once again, it could go this way or it could go that way. So if it goes this way, it's going to be positive Gs. If it goes this way, it's going to be negative Gs. I don't know many pilots that feel they would be operable with minus 6 Gs. The positive you could probably handle. Here's the problem, is that if you abide by this and you slow down to 224 knots, it'll take you forever to get to the runway, and you may not have the hydrazine. So you had to choose between saying the hell with it and I'm going as fast as I can to get there to reduce the time to landing, or you're going to slow down to provide a potential escape should it quit. The same thing applied to a hydraulic failure. Because if a hydraulic failure and the controls don't work, the airplane was going to depart and very, very quickly. I included this because it's important that I don't want to be using terms that people aren't totally familiar with. So some of these are dictionary terms. The first one is you never want to hear an engineer describe something as going to happen as going to be abrupt. And it just says it's going to happen suddenly without any warning. Divergent, I think we're familiar with that. It just says it continues to build an amplitude. It just says once it starts this way, it's going to continue to go that way. Nonlinear. I thought a good way to explain this would be a ladder. If you had a ladder and a conventional ladder, and the steps were all 1 foot apart, and you had a requirement to get up 10 feet, you'd know you had to go 10 rungs because it's linear. Every step is the same. Nonlinear, it says The first step might be a foot, the next one might be 3 feet, and the next one is 2 feet. In other words, you can't look at the bottom and extrapolate how to get to the top. You've got to work your way up and find out. And there's a lot of characteristics in the X-29 which were that way. They were nonlinear, which meant that all the flight clearances had to be very relatively small increments. Catastrophic, this came right out of the dictionary, extremely harmful. I wouldn't argue with that one. The next three don't have anything to do with the X-29, but I love them. I thought I told you not to do that. You don't ever want to have an engineer tell you that. You never want the engineer to say, what the hell happened? And then, this doesn't apply to X-29, but when you got two pilots, you never want the guy at the controls to say, watch this. Flight test challenges. Static divergent, as we talked about, it's encountered as abrupt, divergent, and catastrophic. And predicting it is as a function of increasing airspeed is a nonlinear thing requiring the small bites. So obviously the engineering mind said, well, how are we going to predict where this is going to happen? Because it was an unproven science. And they said, don't worry, we're going to use the Southwell analysis. And I said to myself, that's really good. This is something that just, with the help of a Cray computer, they've developed this analysis and everything's going to be fine. Well, it turns out the Southwell technique was developed in 1932. And it's used to predict bending in beams. So that was not a big confidence builder, but in the end, it worked out. I love this. This is a NASA engineer's description of structural divergence, and I'm not going to ask you to read the whole thing, but I love the last one. The aerodynamic load coefficients with respect to angle of attack are infinite at the critical condition. That's not good. So then I said, this is the pilot's description of structural divergence. Stay away from the critical condition. If you inadvertently reach it, the pain will be mercifully short. And we suggested they install a quick reaction reel in the floor of the cockpit with a cable attached to the pilot's neck. And he said, well, what do you want that for? He said, that will be your best opportunity to kiss your fanny goodbye should something happen. Always good news. The good news came when they did the analysis. They said, within the flight envelope of the X-29, structural divergence, we're not going to encounter it. They were very, very confident of it. So about the time we were celebrating that, they said, however, we've looked at this thing, and now we're concerned that the higher dynamic pressures are going to reduce the natural frequency of first wing bending mode to the point where it could couple up with the fuselage ridge body pitch mode. Not important you understand that. The next one is, result would be abrupt, divergent, and catastrophic. And did I mention predicting the boundary is also nonlinear? Not good news. As it turned out, this was handled very, very well. And once again, because of the real-time data analysis. Grumman's intent was, once we started flying at Edwards, that we were very interested in getting the first 4 flights out of the way. And there's a lot of reasons for that, but one of the primary one was Grumman was footing the entire bill on this fixed price contract until that 4th flight was completed and the airplane transferred over to custody. So they were really, the plan was after the first flight, we were going to turn the airplane around. It came back without any discrepancies. We were ready to go for the second flight, and it snowed at Dryden. So everything came to a halt. And then the weather warmed up, so what do you suppose happened to the dry lakes? They became lakes, not dry lakes, lakes. So this is a slide we just made up. This is Rogers Dry Lake, and just give them a hard time about a boat going across the dry lake. Really wasn't all that bad. But the second flight, the first flight, if you remember, was early in December. Second flight, February 4th, because of the weather. Because not only did the snow have to go away, the water had to go away, so that we had the dry lakes. I call it the bleeding stops. The second flight was on the 4th of February, the third flight on the 22nd, and I had the opportunity to fly the fourth flight on the 1st of March. The airplane was transferred over to the government, and over a span of 4 years, the number one airplane flew 242 flights for 178 hours. Logical question, how does it fly? As a fighter pilot, what's not to like about this airplane? It's small, it's good looking, has sparkling performance, greater than 1-to-1 thrust-to-weight ratio at takeoff. But the interesting thing was there's a lot going on in the airplane, as we've covered, with the three axis, or the three control surfaces and the longitudinal axis and everything else, transparent to the pilot. The canard activity. Canard is the one control surface you could see from the cockpit. And when I flew my flight, I said to myself, I'm going to look out there at the canard, and that little mother's going to be just working his little butt off, because that's the only thing that's stabilizing the airplane. And I said, it's going to be interesting to see all this going on and what have you. And when you're just flying a level flight, the canard was rock solid. You couldn't see any motion in it. That's not to say there wasn't any, and because it's getting updated 40 times a second. So obviously when you maneuver, you could see motion in the canard, but other than that, it was just rock solid. It made it a different airplane, particularly because we primarily use T-38s as chase airplanes. And when you get them side by side at any given airspeed, particularly a slower airspeed, as you might expect, the T-38 was somewhat cocked up. The X-29 would be sitting beside it flat because of all the variable camber and what have you. It just optimized it and what have you. And same thing in turbulence. The one thing about the Edwards test range is turbulence is really quite common. And there were some times where I came back with the airplane and said, I was getting bumped around because you're trying to get stabilized at a particular airspeed and everything else. And the other chase guy said, you are having a problem. You should have been in my airplane. So it really was a delight to fly. Okay, a quick brief on the appearance of aircraft number 2. Aircraft number 2, the contract to build 2 airplanes, I think was concentrated more on, look, we're building one-of-a-kind airplanes. If we lose the first airplane, then we can't be dead in the water. All this is invested, and we got to have another vehicle we can continue the program. But as aircraft 1 proceeded on, it was doing so well and what have you that people started thinking, you know, we really need to look at another potential benefit of forward swept wing, and that's in the high angle of attack area. And as most people here know, that if you're going to be serious about aggressively attacking the high angle attack area, typically they put a spin chute on the airplane. If you're not familiar with it, you can think of it as a small parachute that's in a canister on the back of the airplane. If everything goes to pot and the airplane is out of control, you can deploy this, it comes out, it stabilizes the airplane, and you don't use it to bring the airplane to the ground, you jettison it at that point, but you have regained control of it. So the program was decided to put a spin chute on the number 2 airplane. It was not a cheap deal. And then a decision was made, okay, we're going to complete number 1's program and then activate number 2 because of the 2 airplanes that you could use one to support the other in terms of parts. So that was the decision, and aircraft 2 came out to Dryden the same way that 1 did on a ship, and it flew for the first time in 1989. So how robust was the airplane? I can tell you that from the beginning, you had a gazillion engineers looking at their tables, and you couldn't go anywhere if the instrumentation was not functioning properly. Number 1's program was essentially over envelope expansion, and someone decided it'd be neat for the airplane to appear at Oshkosh at the Experimental Aircraft Association. And when someone said that to me, I said, unless they got a way of getting the ground station out to Oshkosh, it's not going out there. The Air Force will never buy it. The Air Force said, yeah, it's okay with us as long as it goes to Wright Pat for the Dayton Air Show before it goes to Oshkosh. So number one, they had to take all the parts back off a tube, put them back on one, get one back up in the air, and then they flew one back to Wright Pat, and then flew it to Oshkosh, and then it came back again, where they had to do the part swap back again to get number 2. Fine. The high angle attack program, I'm just going to cover it real briefly. It flew again, 110 days that were interrupted because of the PR thing of taking it to the air shows. The program took 85 flights for the high alpha part of it, 70 hours, and it flew its last flight in 1992, which for the X-29 program was 8 years. So the results of it, it turns out the benefits were there. Everything they said, the benefits of high angle of attack, at high angle of attack of a forward swept wing, it had very, very good lateral control. Typically, most high-performance airplanes, when you get into the real high alpha region, you maneuver laterally by generating yaw on the airplane. In the X-29, because of the forward swept wing, it retained the flaperon control and what have you, and it was deemed predictable and usable up to 45 degrees. They reached a maximum of 66 degrees, which doesn't really mean a hell of a lot. But what they did do is they put military aviators, test pilots, to evaluate the X-29, and they flew it against the NASA's F-18 and what have you. And their conclusion was that the X-29's high alpha characteristics were superior to the current frontline fighters. They consider the X-29 a simple airplane because what you're looking at, and I think we'd all agree, is that you have thrust vectoring, which is very, very powerful for high angle of attack maneuvering and what have you. However, it requires a whole lot of complexity in the airplane and the mechanization of the thrust vectoring. So by comparison, the X-29 was considered simple. Okay, where are they now? Total program, 434 flights. That was a record for the X-planes. I think the record was previously held by the X-15, which actively flew 3 airplanes, and there were somewhere around 300 flights. The number 1 airplane was inducted into the Air Force Museum at Wright-Patt. I went out for the induction, and I was talking to him, and I said, how'd you get it here? Because there are no ocean freighters that go to Wright-Patterson Air Force Base. And he said, we trucked it. I said, I'll be darned. We looked at that, and we didn't think it was feasible because of the height, with the wings. And he said, oh, we sawed the wings off. So they sawed them off and hauled it out there and then glued them back on. So obviously it's not a flight article anymore. The number 2 airplane remains up at Dryden. I think you can see it on a static display. It's non-flyable. Okay, the burning question I'm sure people have, if this thing is so good, then why don't we see more modern day airplanes? These are my opinions. The DoD has gone big time into signature stealth airplanes. Forward swept wing is not a good configuration from a stealth standpoint. They'd like to avoid any kind of junctures on the airplane and what have you. Also, it would require, in a fighter competition, it would require a big gamble because we don't pretend the X-29 investigated everything associated with a forward swept wing. Will we see it in the future? It's been on cruise missiles, what have you. The benefits are there. Whether from the stealth standpoint and everything else, I don't know. The Soviets, interesting enough, developed a Sukhoi S-37, which bears a remarkable resemblance to the X-29. It's a much bigger airplane. It's twice as big, and it's got a lot more thrust. And it has two vertical tails. That's primary from an outside standpoint. Did the Russians, the Soviets, benefit from the X-29 program? All I can say is that nothing appeared to be classified on the X-29 program. The agreement was that all the data would be shared with all the U.S. aerospace companies. So there wasn't going to be any benefit to Grumman alone by having this program. And we held frequent briefings where, as far as I know, anybody that was interested could come and listen to them. So whatever they needed to know. In all fairness, the German bomber that I mentioned earlier eventually went to Russia, and when the Soviets came in World War II. So it wasn't their first dance with forward swept wing. Conclusions, the program extended over 8 years. The predicted performance gains were met or exceeded. I don't want to quantify these because The initial generalization was like a 10% improvement. I know we met that. I think we exceeded it. I have seen estimates as high as 30%, which is probably an exaggeration. But the whole program was 434 flights, set a next plane record. The people that designed, built the airplane, my hat's off to them. The airplane was exceedingly reliable. Very, very typical with X-planes is you get them out to the runway and something's not working and it goes back in the hangar and what have you. Ours, typically it didn't have in-flight refueling capability, so we would fly multiple flights in a day. And because it had the flights varied roughly an hour to 1.2, something like that. So the airplane would land, it would taxi into the runway, you would put power on it so the flight control system didn't get powered down, refuel it, crank it back up, and off it went. And so there were days where the airplane was flown 5 times in a row. So real attaboy to the people of that. The advanced computer simulation was validated. It did all kinds of new stuff, and I think it changed people's minds in a lot of it. And then the other thing that needs to be mentioned is the team concept. I mentioned all those acronyms. Nobody ever thought it was going to be as seamless as it was. And I can speak from a flight team, pilot standpoint, because we had on any given time multiple pilots. We all got along. We all were pulling for the other guy and what have you. And so management of the X-29 program, whether it be on the government side or what have you, claim the right because it was such a successful program. I tend to think the people, and I'm speaking about the engineers, the maintenance guys, the guys who built the airplane, everybody was on the same page, everybody was pulling for the other guy, and nobody wore a badge that I'm from this organization and this is the way we're going to do it. So it can work, but it's very people dependent. So that's kind of all I've got. I'd be happy to open the floor to any questions. Anyways, the question was, did we ever have to use the EPU in anger? And the answer is no. Once again, I think the 404 engine, General Electric, it's a good engine. There was little to be proved by intentionally trying to do it. Just as you're probably aware is that back on the F-14 program, we lost our high alpha airplane, not because of anything of the airplane, it was because the EPU, the hydrazine fire. The question was that what is the runtime of the EPU? And basically because of the size of the X-29 and the room available, they had to take the fuel capacity of the F-16 and reduce it by 25%. So, basically it wasn't a bulletproof solution, but in most cases, because of the area we were operating in, there was a dry lake there. And I think most of the pilots really felt, if I had a problem, the hell with the 224 knots. I'm just going to stick it down there and get it on deck. So the question is, how many stops did it take to get the X-29 to Wright Pat and essentially to Oshkosh and back home? Somewhere between 42 and 43. I'm kidding. My recollection is it was 3 legs out and 2 legs back. In the 1 leg between Wright Pat and Oshkosh. Does the plane have an afterburner? The 404, it was afterburner equipped. The airplane was cleared out to 1.6 Mach number, so obviously we used the burner out there and to get there, but as far as normal takeoffs, military power was more than required. And I think we did 1 flight where we did a burner takeoff and then a burner climb, and the chase was damn near still on the runway, so it's counterproductive. The question is, what was the turn radius of the airplane? The airplane was optimized, if you will, in its current configuration. We're talking about pretty much low-speed maneuvering in the high alpha program. And what they found that it could turn inside anything that we had. The answer, though, says that's not important because we're not going to get into a phone booth anymore. And it's a very efficient airplane in there. And so I don't think anybody ever measured it, but when they did a setup with a, say, 2,000-foot separation, the X-29 would dominate any other airplanes. When you moved out, and the other airplanes could take advantage of a higher speed and stuff like that, then it was not as dominant. But the point of the whole evaluation was, are the benefits of the forward swept wing real? And the answer was yes. Did anybody ever roll the airplane? This is a baited question. And I might as well tell the story. I debated it, and I said, I'll stay away from it. But historically, he gets me in trouble every time anyways. The original schedule, as I said in the presentation, Grumman was going to fly the first 4 flights. And I was the project pilot and our chief test pilot. I referred to them that has the goal to make the rules. And so he decided he was going to fly all 4 flights. And I would get my first shot at the airplane, joining the rotation with the NASA guys and the Air Force guys. So Chuck flew the first 3 flights. And on the way back of third flight, he chose to do a roll with the airplane. At that point in the build-up program, the airplane had never been inverted and what have you. I don't know if he was influenced by my suggestion or whether you know, there's always historical things about Scott Crossfield rolled the X-15 and the 707 rolled over Washington, Lake Washington. It was unannounced, and under the NASA Air Force rules, absolute no-no. So they elected to ground him, which left us with a flight and no pilot. Well, no, I was the other pilot, so I got to fly the 4th flight. And anyways, and then Chuck rejoined the program after that. But I did suggest it to him. All right, thank you very much.
Thank you for watching Peninsula Seniors Out and About. I'm Betty Wheaton. See you next time.